In today's session, we are going to see about Module 3 heat exchangers. Generally, heat exchanger is a device which is used to transfer heat between the two fluids when there is a temperature difference. Basically, we can classify the heat exchanger based on its construction and flow arrangement. Based on the construction, so we can classify it as a double pipe heat exchanger and shell and tube heat exchanger. And based on the flow arrangement, we can classify it as a parallel flow, counter flow, and cross flow. Parallel flow in the sense both hot and cold fluids will be flowing in the same direction. And in the counter flow type, if any one of the fluid direction is changed, so that means both the fluids will be flowing in the opposite directions. And in the case of a cross flow type, so one of the fluid will be flowing perpendicular to the other fluids. So we'll have a classification based on this construction and flow arrangement. And regarding this double pipe heat exchanger, so as we have seen parallel flow and counter flow. If you see this arrangement of your parallel flow and counter flow here, as this diagram shows here, the hot and cold fluids enters in the same direction and it leaves at the other end the same direction here. So when the fluids are flowing here, so because of the temperature difference, the heat may be transferred here. When you observe this, the temperature distribution here, so we'll have a maximum temperature difference at the entry, and the temperature difference is keep on decreasing when the fluid is coming out here. So when you see our counterflow type heat exchanger, as we are seeing in this diagram here, the hot fluid is entering on this left hand side and this cold fluid is entering on this right hand side here. So both the fluids have to flow in the opposite direction and it leaves its respective other ends here. And if you see your temperature distribution diagram for this counterflow type, so we'll have a temperature difference almost same between inlet to the outlet here. So from these two temperature distribution diagrams, so we can infer that the temperature difference for the parallel flow type is maximum at the entry and it keep on decreasing when it comes to the end here. But in the case of a counterflow type, the temperature difference remains almost the same between this inlet to the outlet here. So that makes a lot of difference when you consider the performance of your parallel flow and counterflow type. So this equation depicts uh, the heat transfer equation, so which we'll be using for heat exchangers, which refers Q equal to UE delta Tm. So Q stands for heat transfer rate and U is the overall heat transfer coefficient and A is the surface area of the heat exchanger and delta T is the temperature difference, mean temperature difference between the fluids. These three parameters are directly proportional to the heat transfer. So higher these three parameters uh, will have a higher heat transfer rate. By seeing this temperature difference for this parallel flow and counterflow type, since the temperature difference in the case of a counterflow type is remains same almost, so that the Q will be higher when compared to your parallel flow type because the temperature difference is decreasing progressively when it goes to the end here. So it is very clear that your counterflow type will give you a relatively higher heat transfer rate when compared to the parallel flow type for the same heat transfer area. And in the case of a cross flow type heat exchanger, basically two fluids uh, will be using it. Generally, if you think of a cross flow type heat exchanger, so immediately we can imagine the radiator which we are using in our automobiles. So that is a very good example for cross flow type heat exchangers. And in the case of a cross flow type heat exchanger, so we'll have two types, namely both fluids unmixed and one fluid is unmixed here. So in the case of both fluids unmixed, if you see this diagram here, so we'll have a tubes and we'll have a the plates plates which will carry the gas flow on the other side there. By seeing this diagram here, we can say that the fluid particles which is moving on, just moving through these tubes, will not mix with the fluid particles which is moving through the immediate next tubes there. Similarly, when the gas is flowing between the plates here, the gas molecules which is flowing on this side will not mix with the gas molecules which is flowing adjacent to this plate here. So in this way, we say both fluids unmixed here. But in this case, the tube fluids will not mix with each other. So we call it as one fluid is mixed, and when the gas is flowing perpendicular to this, so the gas fluid molecules have not separated as we are seeing in the previous diagram here. So the gas molecules will mix with each other. So we call it as a one fluid is unmixed here. So it gives a comparative performance that we are going to see it later. And coming to the next type of heat exchanger, we call it as a shell and tube heat exchanger. If you see this double pipe heat exchanger, uh, in our previously we have seen, so we'll have a concentric pipe and heat will be transferred and the fluid is flowing through this concentric pipe here. So in the case of a shell and tube heat exchanger, so we'll have an outer shell slightly larger and we'll be having very small number of tubes. The tubes will be more than one, which would have been placed inside the shell here. And generally, the fluids will be allowed to pass through the shell and also the tubes here. So we'll have both fluids inlet and outlet here. And when the shell fluids are flowing, baffles have been provided to change the direction of the fluids so that we can provide turbulence for those fluids, so which will enhance the heat transfer rate here. So it has been found that the shell and tube heat exchanger relatively give a higher heat transfer rate when compared to the double pipe heat exchanger. Besides, it will occupy relatively less area compared to the double pipe heat exchanger here. So with less space, so it can give relatively higher heat transfer rate compared to your double pipe heat exchanger. So what you are seeing is some of the images of your shell and tube heat exchangers. And in the case of shell and tube heat exchanger, so we'll have multi-tube process and multi-shell tube process here. So this shows that we'll have tube pauses more than one pause here. So this is your single pause tube and this is your multi-pause tube. So the heat will be transferred during this multi-process. So we'll get an enhanced heat transfer. On this diagram, we'll have shell fluid will be having only one pause. We can also enhance the number of shell passes. So we'll have multi-shell passes. So this arrangement shows that we'll have multi-tube passes and multi-shell passes. So which will have a relatively higher heat transfer rate compared to your multi-tube passes here. So where we need a higher heat transfer rate, so we'll go for these multi-tube passes as well as multi-shell and tube passes. So this diagram shows the images of your multi-tube pauses and multi-shell pauses. I hope we got some basic understanding of heat exchanges. So now we'll go to the analytical part of our heat exchanges. Coming to this analytical part, there are two types of heat exchanger analysis. That is the thermal design of heat exchanger. One is we call logarithmic mean temperature difference. Simply we call it as LMDD method. And another one we call it as NTA method, number of transfer units. So the number of transfer units method we are going to see it later. So coming to this logarithmic mean temperature difference. So when you see the heat transfer equation for heat exchanger, as we have seen previously, so it refers Q equal to UA delta T. So the delta T refers the temperature difference between inlet and outlet, terminal temperature difference between the two fluids. So that can be used if it is a solid, just we can use the terminal temperature difference. But coming to this fluid here, so there will be a continuous variation of temperature difference between inlet to the outlet. So it would be appropriate, we need to consider the variation of temperature, continuous variation of temperature from inlet to the outlet. So that will take the form of a log. We call it as a logarithmic mean temperature difference. The expression what we are getting it in the form of a log, and it will account the continuous variation of temperature from inlet to the outlet. So on seeing this diagram here, so uh, we have considered hot and cold fluids. Both are entering in the same direction, considering a parallel flow arrangement here. And temperature distribution has been shown here. And we consider the capital T as the hot fluid temperatures and small t refers the cold fluid temperature here. And this graph shows the hot fluid temperature is keep on decreasing from inlet to the outlet, and your cold fluid temperature is increasing from inlet to the outlet, small t1 to small t2 here. And we consider a small elemental area of heat exchanger here. Its length is dx here, and the change in temperature for the hot fluid, when you consider this elemental area, is T capital T, and for this cold fluid it is T small t here. And we consider mass flow rate of the hot and cold fluid as m dot h and m dot c, and specific heat of hot and cold fluids we consider as cph and cpc here. And there is another terminology we'll be using in the case of a heat exchanger. We call it as a heat capacity rate. So that is the multiplication of mass flow rate and specific heat of the respective fluids there. So this we call it as heat capacity rate. So when consider this heat transfer equation for the heat exchanger, when we consider the elemental heat exchanger area dA here, so that can be given as dq equal to UdA delta T here. And we can consider the energy balance equation for this heat exchanger, and that is heat loss by the hot fluid equal to heat gain by the cold fluid here. So we can write this energy balance equation in terms of hot and cold fluids here. As we are saying it, mass flow rate into specific heat, temperature difference of the hot fluids, and this is for the hot fluid, and for the cold fluid, mass flow rate and specific heat of the cold fluid and temperature difference. This mass flow rate into specific heat of the fluid can be written in terms of heat capacity rate, which is for the hot fluid and also for the cold fluid here. So what we do here, we'll just multiply this minus sign so that your for the hot fluid, so that your Q will be positive here. And we can write in terms of the elemental area dq equal to minus ch dt and cz dt here. And from this we can write capital dt equal to minus dq by ch and d small t equal to dq by cc here. Subtracting these two equations, we can write d of t minus t equal to minus dq. Can be taken outside. We can write 1 by ch plus 1 by cc. And we know that dq equal to uda delta t, that we'll substitute here. And we'll bring this delta t on this left hand side here, skipping the temperature difference on the left hand side, writing the other terms on the right hand side here. This relation is for when we consider an elemental area of heat exchanger. And for this entire heat exchanger, we'll integrate for this whole area and also the temperature difference of uh, delta T1 to delta T2, that is from inlet to the outlet. So having integrated this, so this one we can write so 1 by t minus t d of t minus t can be written as ln of t minus t with its limits. Similarly, this u and ch cz remains constant here. Take it outside here, and we can integrate this dA and this t minus t can be written as delta t, as we are seeing in this temperature distribution diagram. And this dA can be integrated. This will be a with its limits 0 to a here. So on substituting the limits, we'll get ln of delta t2 minus ln of delta t1. And this here the limit can be substituted. This will be a minus 0 here. And the ln of delta t2 minus ln of delta t1 can be written it as ln of delta t2 by ln of delta t1. And we can simplify this one as u minus ua 1 by ch plus 1 by cc. And from the energy balance equation, so we can write q equal to ch into T1 minus T2, and this is for the hot fluids, and cold fluids we can write q equal to cc small t2 minus T1 here. And we can keep ch on the left hand side, writing the other terms on the right hand side here. Ch equal to q capital T1 minus T2 and cc equal to q small t2 minus T1 here. So we'll substitute these two equations 4 and 5 in 3 here. Substituting this, then we'll get ln of delta T2 by delta T1 minus UA into capital T1 minus T2 by Q plus small t2 minus T1 by Q here. So this term can be written it as minus ln of delta T1 by delta T2 here. We can cancel this minus sign on both sides here, and we'll take Q outside, and we'll write T1 minus T2 plus uh, small t2 minus T1 here. And we can rearrange this expression on this right hand side in more convenient form. And also this left hand side will write delta T1 as capital T1 minus small t1, and delta T2 as capital T2 minus small t2, as we have seen in the, as we are represented in the temperature distribution diagram here. And here we'll take we'll write this as capital T1 minus small t1 and minus of capital T2 minus small t2 here. And keeping this q on one side and writing the other terms on the right hand side here, and grouping our temperature distribution, the temperature difference on one side here, then we'll have an expression q equal to ua capital T1 minus small t1 minus capital T2 minus small t2 by ln of capital T1 minus small t1 by capital T2 minus small t2 here. So this entire term can be written it as delta T Lm, temperature difference in logarithmic form. So this expression we call it as LMDD for a parallel flow type, temperature difference, logarithmic mean temperature difference for a parallel flow heat exchanger. Let us solve one problem on this heat exchanger having understood the expression of our LMDD. So let me read this problem now. In a double pipe counterflow heat exchanger, 10,000 kg per hour of an oil having a specific heat of 2095 joules per kg Kelvin is cooled from 80 degrees Celsius to 50 degrees Celsius by 8,000 kg per hour of water entering at 25 degrees Celsius. To determine the heat exchanger area for an overall heat transfer coefficient of 300 watts per meter square Kelvin, take Cp for water as 4180 joules per kg Kelvin. So in this, the type of heat exchanger is double pipe and the flow arrangement is counter flow. So we have been given uh, the properties of hot and cold fluids here. Since the oil temperature, entry temperature is 80 to 50 degrees Celsius, water temperature is 25 degrees Celsius. So oil will be the hot fluids and water will be the cold fluids. So in any heat exchanger problems, we need to first identify the hot and cold fluids. Accordingly, so we'll write the data given. So the hot fluid would be oil and the cold fluid will be water here. And the mass flow rate of the oil, so which we considered as hot fluid, it has been given as 10,000 kg per hour. So we can convert in kg per second here. And the specific heat of oil CPH has been given 2095 joules per kg Kelvin. And inlet and outlet temperature of hot fluids were given, that is 80 degrees Celsius, capital T1, and capital T is 50 degrees Celsius. And the mass flow rate of water, which we consider as cold fluid, has been given 8,000 kg per hour, which is 2.2 kg per second. And the cold fluid entry temperature is 25 degrees Celsius, and the overall heat transfer coefficient is 300 watts per meter square Kelvin. And the specific heat of the cold fluid is 4180 joules per kg Kelvin. So we need to find out the heat exchanger area. So for this, let us first consider the energy balance equation. It is heat loss by the hot fluid equal to heat gain by the cold fluid. So writing this expression for the hot fluid as well as for the cold fluid here. So in this expression, we know, So all the parameters except small t2 here. So we need a small t2, I mean all the four temperatures to calculate logarithmic mean temperatures, LMDD for this counterflow type here. So substituting all the values here, the unknown T2 can be calculated, which is 44 degrees Celsius. And for calculating our logarithmic mean temperature difference for this counterflow type, so we'll write this expression. So this expression is available from our heat and mass transfer data book in heat exchanger type. So we'll write this expression capital T1 minus small t2 equal to capital T2 minus small t1 ln of capital T1 minus small t2 by capital T2 minus small t1. So we'll have all the temperatures. We'll substitute this and we'll get logarithmic mean temperature difference as 30.16 degrees Celsius. And using our energy balance equation, either for a hot fluid or cold fluids, so we can calculate the amount of heat transferred Q. Substituting the values, we have got Q equal to 174.72 into 10 power 3 watts here. So writing the heat transfer equation for this heat exchanger Q equal to UA delta TLM. This equation is also available in our heat and mass transfer data book. So in this expression, we know Q and overall heat transfer coefficient and LMDD. So the unknown is heat exchanger area. So we'll get our heat exchanger area as 19.3 meters square. So by using the heat exchanger equation and also the LMDD expression, we can able to get the heat exchanger area for this problem. So we'll see one more problem. Hot oil with a capacity rate of 2500 watts per Kelvin flows through a double pipe heat exchanger. It enters at 360 degrees Celsius and leaves at 300 degrees Celsius. Cold fluid enters at 30 degrees Celsius and leaves at 200 degrees Celsius. If the overall heat transfer coefficient is 800 watts per meter square Kelvin, so we'll have to determine the heat exchanger area required for parallel flow and counter flow here. So we are using two fluids, oil and another one they mentioned it as cold fluid here. In this problem they given a heat capacity rate. So that is they given capital C values for the respective fluids here and the temperature. Hot fluid inlet and outlet temperatures have been given and cold fluids inlet and outlet temperatures were also given here. And we have been also given overall heat transfer coefficient. So with this we'll proceed to find out the heat exchanger area for both parallel flow and counter flow type. So writing the expression for parallel flow Q equal to QA delta TLM. This expression we can get it from our heat and mass transfer data book. So for this we need to know LMDD value. So writing the expression for this LMDD value. So capital T1 minus small t1 minus capital T2 minus small t2 ln of this temperature difference here. So we have all the four temperatures here and we have substituted hot fluid inlet and outlet and also cold fluid inlet outlet temperatures here. Substituting the values, so we are getting the logarithmic mean temperature difference for this parallel flow as 192.64 degrees Celsius. And writing the heat transfer equation for this hot fluid from our energy balance equation, Q equal to capital CH and capital T1 minus capital T2 here. So we'll get the heat transfer rate as 150 into 10 power 3 watts. So in this expression, we know Q as well as the overall heat transfer coefficient, and we have calculated temperature, logarithmic mean temperature difference. So the unknown value of A can be calculated, which is 0.973 meter square. So this value we have calculated for parallel flow heat exchange. And coming to this counter flow type, so we'll write the heat transfer equation for this heat exchanger Q equal to UA and delta TLM. And writing the LMDD expression for counter flow type. So we can write from our heat and mass transfer data book here. So substituting the values of this temperature difference here. So we'll get our LMDD value for counter flow type as 210.2 degrees Celsius. So from our energy balance equation, we have calculated Q, and writing this expression Q equal to UA and delta TLM, so that we can write this expression as, and we can substitute the values here. So the Q is 150 into 10 power 3, and overall heat transfer coefficient has been given as 800, and area to be calculated, and logarithmic mean temperature difference we calculated as 210.2. So we got the area as 0.891 meter square here. So comparing the values of area for both parallel flow and counter flow type for the same temperature difference. So we got for the parallel flow as 0.973, and for the counter flow we got 0.891. So it is very clear that for the same temperature difference, for giving the same heat transfer area, I mean for the same heat transfer rate, uh, the area required for a counter flow is relatively less than for parallel flow type. So the heat transfer area, since the heat transfer area required is less here, subsequently from this area we can calculate the diameter and length of the heat exchanger by writing the surface area as pi dl. If it is a shell and tube type, we'll write number of tubes and number of passes. We'll incorporate the term of n and number of tubes and number of passes here. So when the area is less here, your physical size of the heat exchanger will be less. So it occupies less space, and also since the physical size is relatively less, so the cost will also be less here. So it is preferable to use counterflow type of heat exchanger compared to your parallel flow type heat exchanger, so giving relatively better heat transfer performance. And coming to this, the next type of heat exchanger, so we'll have condenser and evaporators.